You guys didn't miss much, but some good jokes. All right. So the name for both of these molecules is 3-chloroctane. I got about half of you saying, yeah, those are the same. You can superimpose those two structures, and about half of you saying you can't. By drawing what? Cool. That's what we're gonna. That's the end of the class. You can do that. You can also just try to fit them. So if I take the top molecule and I lay it over this bottom one, the carbon chain's superimposed. All right, but the chlorine would be out in one and back in the other. To make the chlorine back, I'd need to flip the molecule over. So here's the thing: when you're trying to superimpose two structures, you can't do anything else. You got to treat it like a block. Right? So if you can't, like, I'm going to rotate here, I'm going to switch these. You can't break a bond or make a bond. You just have to take the structure. You can look at it from the other side. You can look at it from the top. Do whatever you want like that. But the molecule itself has to stay the same. So in fact, these are not superimposable. We're going to get into this in chapter 5. I'm kind of getting ahead of the game a little bit here. These are what we would call stereoisomers. They are isomers that differ. So anything that is called an isomer will have the same molecular formula. All right, so that's the first thing, right? If one of those molecules had an O and the other one didn't, they're not isomers. If one has 2 chlorines and the other has 1 chlorine, they're not isomers. But they have the same number, they have the same molecular formula, but they're connected the same, chlorine on carbon 3. But, oh crap, we can't superimpose them. So 2 molecules with the same connectivity, same molecular formula, but they're not superimposable, are called stereoisomers. They really only differ in how they're arranged, the atoms are arranged in space. And we will get to this. You have to account for this in nomenclature. So there's a nomenclature feature for each of these. And we'll figure out how to do that. All right, you could look at Newman projections. Yeah, and so Newman projections are the next thing we're going to do. I'm going to put ChemDraw back on the board. Let the folks at home see the Wake Forest banner here for a minute. Hopefully that stays in focus. Guys at home, I don't know how well this is going to work. You see that? That's an actual chemical thing. You ever drop a flask or something glass? You can do this at home too. You can't possibly reach down in time to catch it. If you catch it on the top of your foot, lay it on the floor. Did that on purpose. All right. Okay, so here's ChemDraw. Yeah, I'm going to have to work over here. So get rid of. Oh, I wanted to show you something else about ChemDraw. This is really cool about ChemDraw. Look at this. Convert structure to name. There you go. So this is another reason I don't belabor nomenclature. Professional organic chemists, if we need to name a molecule, draw in ChemDraw, and have a name. All right, all of this is not to say that there won't be some fairly simple molecules on exam 1 I ask you to name. There is a Wiley plus nomenclature assignment. You need to know the basics. But I promise you, I can go far enough with nomenclature that you will not be able to name the molecule. Moreover, I promise you, I can go far enough with a molecule that I can't name, or the chair of the department, Bruce King, can't name. All right, like it's really hard. Yeah, for some reason the thing up top is broken. I don't know what the deal is. Duplicate. That didn't clear it up, did it? Okay, so I'm going to get rid of this thing now. Okay, so now I've drawn butane. I'm going to copy butane, and I'm going to go to this other program called Chem3D. which you will, if you download ChemDraw and ChemOffice, you'll also get Chem3D. I'm going to paste it in. Come on. There we go. And it will draw it in. And so now, right, Chem3D. On this molecule, you don't only get a wedge and a dash where there's a functional group. Okay, so here where there's two hydrogens, one of those hydrogens is sticking out at you and one is going back. A pretty typical way to show a tetrahedral atom on a board is two bonds at the plane, one bond toward you, one bond away. There are a bunch of different ways of doing that, but that's one way. All right, so if you play with these molecules, and I kind of recommend getting this, like you can manipulate these. These are like electronic molecular models. I'm 50 years old, so I really like an old-fashioned just ball and stick molecular model, and maybe you will too. But if you prefer to do it on a screen, that's fine. Okay, so the Newman projection, as someone mentioned, arises by looking down upon. Okay? So it's just a different way. Like, here's one way of looking at the molecule. We can just decide to look down that middle C carbon-carbon bond. And so let's go back to ChemDraw for a minute. I can actually draw butane a different way, not as a zigzag, but like whatever kind of line that is. Copy that. All right, now I've got a different one. Now if I look down that, the methyls are in a different place. All right? What is the relationship of those two molecules? Are they isomers? They have to at least be isomers. They have the same molecular formula, C4H10. Are they connected the same? They are. So some of this is definitions. What do I mean by connected the same? I mean, if you start one place, carbon, you got a CH3, it's attached to a CH2, which is attached to a CH2, which is attached to a CH3. So they're connected the same. Are they superimposable structures? They aren't, right? Like one's all splayed out, one's kind of U-shaped. So in a sense, don't write this down. If you're at home and taking notes, step back for a minute. In a sense, they're stereoisomers. And if you could isolate them like this, they would have different properties because they're different structures. That's sort of the corollary of the fact that structure equals property. If two molecules don't have identical structures, they will not have identical properties. But they may be really, really similar. All right. Okay, now the trouble is, everybody saw how I did that on... All right, I'm going to move off Chem3D, folks at home. So everybody saw how I did that. Let's get back to the board. For our stereoisomers over here, the 3-chlorooctanes, the only way to make them superimposable is to switch the chlorine and the hydrogen. That requires breaking and making bonds. So that would be a chemical reaction. Right? It can be done. Chapter 7, we'll see how you can do that chemically. But a chemical reaction that's a reaction. Isomerism is about comparing molecules just sitting there. And it turns out the two butanes that the people in the room can still see on the screen, the folks at home could have seen, those two butanes can turn into each other just sitting there. The C2, let me draw this. Okay, so we would say that this is an equilibrium. The butane that's more stretched out can turn into the butane that is U-shaped, and then it can go back. And the reason it can do this is the molecule can freely rotate about that single bond. And this is true of essentially, well, 99.99% of the molecules you'll ever see. Carbon-carbon single bonds, actually any kind of sigma bond, molecules can freely rotate about that. Right? If all you have is a single sigma bond, the molecule will freely rotate about it. And it does this, you don't have to do anything. This is what energy is. This is what temperature is. If you're anybody ever, this is a great bar conversation, like what is temperature? What is heat? Right? Heat is molecular motion. So we're all sitting in here right now, it's whatever it is, 70 degrees. We have all these air molecules around us. And, I mean, we are being bombarded. Like, little tiny molecules are flying into your face trillions of times a second. Think of that when you're trying to go to sleep tonight. All right, so that is temperature. Those molecules are also rotating about their single bonds. They're vibrating. They're bending. The bonds are stretching. They're colliding with each other. They're colliding with the walls. So a molecule just sitting around at 20 degrees Celsius will spin around a sigma bond like that a few 100 billion times a second. Right, this is amazingly fast motion. But we can also analyze that. So let's analyze it. Let's put a face right here. So that's an eye. I just drew an eye. I'm a lousy artist. But I mean that to be an eye. And what I mean is I've drawn 4 carbons in the plane of the board here. So there are, right, they're all tetrahedral atoms. So that CH2 at the front, 1 H is sticking out toward you, 1 H is sticking back away. The other thing I mean here, I've drawn this H to the left, that H to the right. There's not a right and a left there. Properly, if we're looking at this molecule exactly so that these 4 carbons are in the plane, one of these hydrogens is directly in front of the other. Right? The hydrogens are right here. That's a crappy way to represent the molecule. These are all symbols. All these molecules I draw are symbols of molecules so that we can talk about their structure, communicate with each other about them. Because remember, the molecules are the molecules no matter what we call them, no matter how we draw them. They're going to do what they do. All of this is so you and I can think about them, right? Because they're way too small. I can't handle it. I can't look at it. And then I can communicate to you my thoughts about it. Okay, so if I were going to draw this accurately, I would have 1 H in front of the other one. But now it's going to be all garbled and confusing, and I can't think about it. I can't clearly communicate to you about it. So we draw it so it's just canted a little bit, side to side. I could have just as easily put the front H on the right and the back H on the left. It would have meant exactly the same thing. All right, same thing here. There we go. So that's, we don't really need to consider the CH3s here. Those are just CH3s. I'll go ahead and draw that in. CH3, CH3. All right. So I've drawn my eye right here. And I'm going to say that carbon 2 that's the front carbon because it's closest to my eye, right? So here we go. That is the front carbon. I've drawn it as a circle. Atoms are not little circles. All right, so that's a carbon atom. Everybody good with that? Stay. Actually, I want more colors. All right, so if my eye is looking there at the front carbon, and now you have to, whiteboards are really good for this, chalkboards are really good. This is kind of a physical thing. This methyl, if I'm looking there, and let's say that I'm on Earth and gravity works, and so I'm standing there looking at it like this. I'm actually looking down at it, and this methyl is going down and coming toward me. Like that. So basically off this front carbon that's tetrahedral, all three of the things, if my eye is here, all three of the things are coming at me. And I'm just going to assume that. I'm not going to like make an effort to show wedges there. Again, I'm here, looking there. This hydrogen, which is sticking out from the board, if I'm in the plane of the board, it's to my right. The dashed hydrogen that's behind the board, if I'm in the plane of the board, is to my left. So I've drawn the front carbon. All right. The back carbon, if I'm here, can I see the back carbon? No, right? That back carbon is behind the front carbon. I'm looking down the bond. My computer, I'm going to have to remember my chords so that doesn't go, or change the settings. Okay, so off this back carbon, I'm looking there, all three of these groups are going away from it. Again, I'm going to assume that. I'm not going to put dashed wedges in there. All right, so there's a methyl that's up. Right? The front H is down to the right. The back H is down to the left. And I've just drawn a Newman projection for butane. Something to keep in mind here. I'm probably going to erase this. Every carbon you draw, every tetrahedral carbon will look like that as a front. Or that as a back. It's always going to be, and then, I mean, you can spin that, you can look at it from any perspective. Again, there's no up or down. Right? So I can just spin that however I like. But it's going to be kind of this, like, a Y, 120 degrees between all of them. They represent tetrahedral atoms. And then, like I said, this bond here, the bond I'm looking down is a sigma bond. So we can freely rotate it. Okay, so it can spin. Now, this is not quantized behavior. This is just like looking down an axle, right? If I went outside and I drew like a single line on a tire, and I said, now follow that and draw every conceivable angle, you have an infinite number of angles to draw. Pointless. All right, so what we do is we sort of say, how far can we rotate and get different conformations that are important? And then we'll kind of mentally interpolate. So let's rotate 60 degrees. And I'm just going to arbitrarily say I'm going to hold the front carbon the same. And I recommend doing this. Right? I could rotate both front and back carbons, but that gets hard to keep track of. I'm going to say just keep the front carbon looking the same and change the back carbon. So I'm going to rotate the back carbon 60 degrees. And again, I'm going to arbitrarily say clockwise. So front carbon, you'll notice the more I do this, the crappier my circles get. Doesn't matter. I'm not an artist, and I don't grade for art. And again, I'm not going to, if we did this exactly, if we were exactly in front of it, we rotated exactly 60 degrees, everything would line up in front of each other. But that's a bad way to represent it. You want to represent it so it's clear. So what I'm saying is this methyl is directly in front of that H, this H is directly in front of that methyl, this H is directly in front of that H. Okay? Everybody up with me on what I've done there? Those two structures. All right. Which one of these do you think is more stable? Got to vote for the first one. Anybody think the second one is more stable? All right. So, yeah, it is. Here's another little principle. If two atoms are not bonding together or some other way of making a positive interaction, you generally want to keep them apart. Okay? So if two atoms are not going to bond with one another or have like a hydrogen bond or a van der Waals interaction or something like that, you don't want to have them together. They're going to clash. In this first one, we've got, the two biggest groups here, the two methyls, as far apart as we can get them. In the second, each methyl is kind of conflicting with an H. Let's rotate another 120 degrees. Each blue equilibrium, and by the way, I did resonance the other day. Resonance is a single arrow with two barbs, and it means these two structures are just different ways of drawing the same molecule. That's resonance. Two arrows, one going left, one going right, says the thing on the left will turn into the thing on the right, the thing on the right will turn into the thing on the left, but they're different. Okay, so an equilibrium arrow, you've got to have different structures there. Okay. So front carbon, like I said, keep the front carbon the same all the way through. All right, so you can just draw in those. Now we got the methyl down here, H's. That's another 60-degree rotation. You can see why we're doing 60 degrees at a time. We go from the bonds are staggered to the bonds are eclipsed to the bonds are staggered. Obviously, there's somewhere in between where like this methyl is here, or here, or there. And it's going to be somewhere in between. If the first structure is more stable than the second structure, the closer we get to the methyl to be in the first structure, the more stable it is. The closer it gets to the second structure, the less stable it is. All right, so the structure I just drew, the third structure, more or less stable than the second structure. Got some lesses, yeah?
Less.
More. Sorry, back? Less. Got lessons. Why are you guys saying less? Because the methyls are closer together. And that is, in two dimensions, true. So there's the part that I said, and everybody nodded their heads, but it's got to stick. And I'm pointing that out not to say, why don't you guys remember this? There's a lot of information. Today's class started pretty slow and is accelerating. There's a lot of stuff to keep up with. The three groups on the front, remember, stick out at you. Three groups on the back, go back. And then there's something else, and this one, I swear, I told you at the beginning of class that all you needed to know about molecular orbital theory. Two electrons in a bonding molecular orbital is a bond. And every bonding molecular orbital has an anti-bonding orbital with it. Turns out that anti-bonding orbital is really important. There is a molecular orbital reason here. These staggered conformations, the electrons in this carbon-carbon bond actually overlap with the anti-bonding orbital of the other carbon-carbon bond. And that's a stabilizing influence. You don't actually need to know that in this class. You can memorize the fact that comes out of this. It turns out that the third structure is a lot more stable than the second structure. That because the bonds on the front are sticking out at us and the bonds on the back carbon are going away, that when the bonds are staggered like this, front, back, they're actually not interacting that strongly yet. Is that a question? Sorry, I don't have your name yet. You had your hand up, or were you just... No? Okay. Question?
So will staggered always be more stable than eclipse?
Almost always. You should definitely go, you should memorize that. I can come up with an exception or two. But they're really weird. All right. My job is, listen, I guess we should, I don't know if this helps you or hurts you. 3 minutes. I promise I can trick you. All right? So a lot of students end up spending a lot of time trying to figure out what their professors are going to do. That is unproductive use of your time. If I want to go design a test with a bunch of exceptions that's really tricky, if I want the average in here to be 12, I can do it. And there's not a damn thing you can do about it. So don't worry about that. Assume I am a man of good faith. All right? I'm going to try to teach you the fundamentals, and I'm going to test you to see that you've learned the fundamentals. So, the perceptive question is, are the staggereds more stable than the eclipsed? Okay, and let me actually define these. So, this is a staggered conformation, and this is an eclipsed. And what we mean by that is, again, a front bond, if we just go around the circle, so let's start up here. Back, front, back, front, back, front. Front and back are staggered. Staggered. We look here, front and back are in front of one another. So the front bond eclipses the back bond. That front group eclipses the back group. Eclipse. As we rotate 60 degrees, we'll go from staggered to eclipsed to staggered. Bad board management here. I said the front stays the same. Can you see this?
Yeah.
Okay. So, staggered, eclipsed, staggered, eclipsed. And again, like I said, the perceptive observation is the 3 staggered conformations, I've only drawn 2 of each here. You can rotate 60 degrees again. Right? If I rotate 60 degrees from that 4 structure, I'll get another staggered. 60 degrees from there, I get another eclipse. 60 degrees from there, I get back to the original. 6 times 60 is 360. Okay, so every staggered conformation, all 3 staggered conformations are going to be more stable than any of the 3 eclipsed conformations. Let's put some letters to this. It's not too complicated. A, B, C, and D. So yeah, conformation C is a lot more stable than conformation B. But your instinct was good, all right? So all of you were like, oh, C is less stable than B. If you flash back to that. Almost all of you enthusiastically told me that the 3rd structure is less stable than the 2nd. And the reason, you said, is that the methyls are closer together. And that is, in fact,